Welcome to our channel Biswanka's Math Exclusive. This is my part 10 video. In this video, I discuss about partial differential equation on Laplace. If y is equal to yxt, then Laplace of del y by del t equals to p y bar xp minus yx0. Number 2. Laplace of del square y by del t square equals to p square y by xp minus p yx0 minus yt x0. This bar denotes the Laplace. Number 3. Laplace of del y by del x equals to dy bar by dx. Number 4. Laplace of del 2y by del x square equals to del 2y by bar dx square, where Laplace of yxt equals to y bar xp. Del y by del t at the point x0 equals to yt x0. Now start the example. Example: del u by del t equals to a square del 2u by del x square, x greater than 0, t greater than 0, which remains bounded for x greater than equals to 0 and obeys the following initial and boundary conditions: u x0 equals to 0, u 0t equals to ft. Taking Laplace transform of the equation and the boundary conditions, then Laplace of del u by del t equals to a square Laplace of del 2u by del x square. Applying the formula, we get p u bar xp minus u x0 equals to a square d square u bar by dx square, or p u bar equals to a square d2u bar by dx square, and Laplace of u0t equals to Laplace of ft, or u bar 0p equals to f bar p. Now d square minus p square u bar equals to 0. Then the auxiliary equation is m square minus p by a square equals to 0. From here we get m equals to plus minus root over p by a. Then the integrating factor is c1 e to the power root over p by a x plus c2 e to the power minus root p by a x. Then u bar equals to c1 e to the power root p by a x plus c2 e to the power minus root p by a into x, where c1 c2 be arbitrary constant, or u bar e to the power minus root p by ax equals to c1 plus c2 e to the power minus 2 root p by a into x. When x tends to infinity, then c1 equals to 0. That is, we get u bar equals to c2 e to the power minus root p by a into x. Again, when x equals to 0, then u bar 0p equals to c2, or c2 equals to f bar p. That is, we get u bar xp equals to f bar p e to the power minus root p by a x equals to f bar p g bar p say, where g bar p equals to e to the power minus root p by a into x. Note: Laplace inverse of 1 by p e to the power minus a root p equals to ft, that is ft equals to 1 minus 2 by root pi integration 0 to alpha by 2 root t into e to the power minus tau square d tau equals to 1 minus phi x, where phi x equals to 2 by root pi in the integration 0 to x e to the power minus tau square d tau is the error function. Let g bar p equals to p into 1 by p e to the power minus root over of p by a into x equals to p into hp, where hp equals to this. Then Laplace inverse of hp equals to Laplace inverse of this. Then solving, again Laplace of h dash t equals to p h bar p minus h0. Again solving, step by step solve, applying the Leibniz formula. Then taking the Laplace inverse. This is the convolution theorem, applying convolution theorem, then solve, we get the required solution. Now start a new topic, define integral transform. The integral transform of a real valued function f(x) of a real variable x is denoted by I(f(x) and is defined by I(f(x) equals to integration minus infinity to infinity k alpha t ft dt, provided the integral is convergent, where k alpha t is the kernel of the transform and is a function of the variable t, and alpha is the parameter independent of t, may be real or complex. Also we denote it I(f(x) equals to integration x1 to x2 k alpha t ft dt, where x1 x2 b2 real constant. Next start Fourier transform. The Fourier transform of a real valued function f(x) of a real variable x is a function of a real variable k and is denoted by fk or fx or capital F small fx, and is defined by capital F small fx equals to 1 by root over of 2 pi integration minus infinity to infinity e to the power I k x fx dx, provided the integral exists. Dirichlet condition. Let f(x) satisfy the following conditions. f(x) defined in the interval open interval ab. f(x) and f(x) are piecewise continuous in open interval ab. f(x) is periodic in open interval ab. Then the above condition is called Dirichlet condition. Then existence of Fourier integral transform. The Fourier integral transform exists if f(x) is integrable in any finite interval. Integration minus infinity to infinity fx dx is absolutely convergent. Integration minus infinity to infinity e to the power I kx fx dx is convergent. Next start a theory. The Fourier transform of a function is bounded if it exists. Start the proof. We have the Fourier transform of a function f(x) is capital F of small fx equals to 1 by root over of 2 pi integration minus infinity to infinity e to the power I kx fx dx equals to fk. Again, since fk exists, then integration minus infinity to infinity mod of fx dx is convergent, and so it gives a finite value. Taking minus infinity to infinity in the integration mod of fx dx less than equals to capital B, a positive constant. Again, integration minus infinity to infinity e to the power I kx fx dx is a convergent. Now mod of fk equals to mod of 1 by root 2 pi integration minus infinity to infinity e to the power ikx fx dx less than equals to 1 by root over of 2 pi integration minus infinity to infinity mod of e to the power ikx mod of fx dx less than equals to 1 by root over of 2 pi integration minus infinity to infinity mod of fx dx as mod of ikx e to the power ikx equals to mod of cos kx plus I sin kx equals to 1 less than equals to 1 by root over of twice pi b by 1, that is mod of fk less than equals to capital B by root over of twice pi for all real variable k. Thus fk is bounded and then the theorem is proved. My topic is end. If this video is helpful for you, please like and share and subscribe our channel for these types of video notification. I regularly upload these types of video in our channel, so please subscribe. Thank you.